So far, we've been focusing on abelian groups, where the binary operation is commutative. A typical example is the group of rotations of a square. It doesn't matter whether you first rotate over 90 and then 180 degrees, or in the opposite order. The result is always the same, because you just add up the angles, and addition is commutative. We then looked at the matrix representations of these groups, and we discovered that we can always diagonalize all the matrices at once. This means that we can find a single basis in which all of the matrices become diagonal at the same time. This allows us to break the representation into smaller parts, each acting only on a single eigenline. And since an eigenline is one-dimensional, these are the smallest parts we can find, because there are no useful dimensions below 1. And so we end up with a set of irreducible representations that all have little 1-by-1 matrices in them. The only thing that really matters here is the number inside each matrix. So we might as well get rid of the matrix brackets altogether, and just look at the numbers themselves. We call this a character for the group. We put all those characters in a table, and this tells us everything we need to know about the representations of the group. Today, we're going to do something similar for non-abelian groups. This will turn out to be a bit more challenging. The main problem is that when your group is non-abelian, you won't be able to diagonalize all matrices. So you can't decompose the representations into one-dimensional pieces. We can actually understand why this is impossible. Say that you have two elements from your group. Let's call them G and H. We represent them with two matrices, capital G and H. The idea is that we want to find a single basis in which both of these matrices become diagonal. So we want a single basis change matrix P that turns both G and H into diagonal matrices. We will call those diagonal matrices C and D. Now let's take the product of our two matrices. The key insight is that we get P and its inverse right next to each other, so they cancel out. That's what inverses do. And now we have two diagonal matrices right next to each other. The simple truth is that diagonal matrices always commute. Their product is also diagonal and just contains the pairwise products of the diagonal elements of C and D. You can do that in either order, so we can swap the order of C and D. They commute. Now we just reintroduce the basis change matrix P and its inverse, and we're done. We have shown that if you want to find a single basis change matrix P that makes both of our matrices diagonal, then the matrices have to commute, basically because the underlying diagonal ones commute. The only way this proof works is if this P and this P are the same matrix. So the conclusion is that only commutative groups can have such a basis change matrix P. Throughout this video, you will see that all of our non-abelian examples will fail to fall apart into nice one-dimensional pieces. Here's a familiar example of a non-commutative group. D4, the symmetries of the square. We have not only rotations this time, but also reflections. The order in which you do your reflections makes a difference, so this group is definitely not commutative. Like any other group, this one also has a trivial representation. We just map each group element to a small 1-by-1 identity matrix. Easy peasy. Here are a few other one-dimensional representations for D4. You can verify that they all satisfy the requirement of a morphism. So far, this is going quite well. We already have 4 one-dimensional representations. But because our group is non-abelian, we won't be able to find 8 of them. A square is a 2-dimensional shape, so it makes sense to transform it using 2-by-2 matrices. We have 4 rotation matrices that rotate over 0, 90, 180, and 270 degrees. And here are 4 reflection matrices that reflect over the horizontal, vertical, and 2 diagonal lines. You can once again verify that this mapping satisfies all the requirements for a morphism. For example, we can either perform this rotation followed by this reflection, and then map the resulting reflection to its matrix, or we can first map 2 matrices and then calculate their matrix product. The result is always the same. The main issue here is that this 2-dimensional representation turns out to be irreducible. It cannot be broken into smaller pieces. There is no basis in which all 8 of these matrices could ever become diagonal all at the same time. Can you see why this is impossible? Apart from the algebraic proof with the inverses that I gave earlier, there is also a geometric reason in this case. I will leave it to you to find it. Leave your best argument in the comments. This completes our list of irreducible representations for D4. 4 of them are just scaling operations on a 1-dimensional eigenline. But the last one is 2-dimensional. It takes place on a 2D plane, not on a 1D line. If we take the direct sum of the 4 eigenlines and the 2D plane, we get a block diagonal matrix. There's no way to get a diagonal one anymore. I want to urge you once again to consider the shape of the data in this matrix. When a diagonal element sits all by itself, we have an axis that doesn't interact with the other axes. The other numbers in its row and column are all 0, so there is no influence between this coordinate and the others. That's why we say that everything happens inside a single line. The 2x2 block also has zeros around it, but there are non-zero interactions going on inside the block. So this time we have a 2D plane in which 2 axes are interacting with each other in a way that cannot be untangled. But they still don't interact with the rest of the space. So unlike an abelian group, a non-abelian group such as D4 can have irreducible parts of a dimension higher than 1. And this raises an important question. How can we turn such a higher dimensional block into a character? In the previous video, I told you that a character is a morphism from a group to the complex numbers. The morphism turns the binary group operation into complex multiplication. The purpose of characters is that they capture all of the important information about the representations of a group. For 1x1 matrices, things are ridiculously simple. To turn a matrix representation into a character, just take the number out of the brackets, and that's all. But this time we have 2x2 and larger matrices. How can we turn those into numbers? The most obvious approach would be to use the determinant. It has many advantages. The determinant of a matrix is a single number, which is precisely what we're looking for. The determinant is also basis independent. When you change to a different basis, the determinant stays the same, so it's very robust. But the biggest plus is that the determinant is a homomorphism from matrices to numbers. That's awesome, because a matrix representation itself is also a morphism. So when going from the group elements to their matrices and then to the corresponding determinants, we string 2 morphisms together. The combination is a new morphism, and that's exactly what we need. A character is required to be a morphism. So I guess this is it. We have found the perfect way to extract characters from higher dimensional matrices, right? Not so fast. Look what happens when we calculate the determinants for all the other 2x2 matrices of D4. The rotations have a determinant of 1, and the reflections get -1. The result is exactly the same as this other character that we already had. So the determinant doesn't manage to distinguish between these 2 rows of the table. That's bad news. The entire point of a character is that it should uniquely characterize a representation. The determinant fails to do that, and not just in this particular example. So, in spite of all its advantages, the determinant is out. Too bad. What else have we got? Well, there's the trace of a matrix. Just like the determinant, it's also a number, and it's also independent of your choice of basis. Unfortunately, it isn't a homomorphism. When you take the product of two matrices, the determinants behave perfectly. They just multiply. But this is no longer true for the trace. You may remember that the trace has a more additive behavior rather than a multiplicative one. So it would seem that the trace is no good either. And yet, look what happens when we take the traces of our 2x2 matrices. Not only do we get a unique row in our table, it's also orthogonal to the others, just like before. We will soon see that all of the miracles are still alive and kicking in this new table. So, quite unexpectedly, the trace turns out to be perfect. I don't have a really convincing explanation for why it works so well. It just does. Maybe it's because we're constructing direct sums and traces behave like sums? I honestly can't say. The only problem is that we no longer have a morphism. But that's cool. We gladly give that up in return for all those miracles. So from now on, we will use a more flexible definition of characters. They are the traces of the representation matrices, and we no longer require them to be a morphism. By the way, did you realize that for one-dimensional representations, nothing has changed? The single number inside the brackets is the trace of the 1x1 matrix. So our new definition of characters is a clean extension of the original definition. That's good. In linear algebra, the trace plays a very modest role. It has no obvious geometric interpretation, and it has very few interesting applications. Just think about how you calculate it. You add up the diagonal elements, but you ignore everything else. You throw away the majority of the matrix elements. And yet, somehow, this is enough to capture all of the relevant information. Just as with abelian groups before, two representations are still the same if and only if they have the same character. That's why the trace is the cornerstone of character theory. To show you all of the miraculous properties of characters, I will put a second table on the screen. This one is for the group D3, the symmetries of a triangle. It contains 3 rotations and 3 reflections. You will also often see it called S3, the group of all 6 permutations of 3 objects. On the left we have the earlier D4 table again, this time with the last row filled in. It contains the traces of the 2x2 geometric matrices that we just calculated. Just as for abelian groups in the previous video, these tables are square. Well, no, not yet. But look at these 2 columns. They're completely identical. All of our characters map the 90 and 270 degree rotation to exactly the same values. And we have more of these duplicate columns in our table. What's going on here? Well, remember, we are building a bridge between group theory and linear algebra. And this is a perfect example of how those 2 domains come together. First, the 90 and 270 degree rotations are conjugates of each other. If you don't know what conjugates are, I urge you to watch our video about non-abelian groups, where we divide the elements of a group into conjugacy classes. The 2 diagonal reflections are conjugates because they are essentially the same if you look at them from the correct perspective. Mathematically, we express this with a sandwich product. 2 group elements are conjugates when one of them can be written as a sandwich with the other in the middle. Again, for more details about how this works, check out the earlier video. Now we cross the bridge from the world of groups into the land of matrices. Our representation is a morphism, so it maps each relation between group elements to the same relation between matrices. So we get the same sandwich product between the two matrices. In linear algebra, the sandwich product performs a change of basis. We have an entire video about that topic if you need a refresher. And now for the main point. When you change to a different basis, the trace remains the same. So we have three important steps. When two group elements are in the same conjugacy class, they are mapped to similar matrices, which have the same trace. And that is why the trace values are identical within a conjugacy class. That's why the 90 and 270 degree rotations have the same values in their columns. It's because they are conjugates. I hope you see that it's pretty cool when so many ideas come together into a single result like this. Well then, instead of listing each element individually at the top of the table, we should list only the conjugacy classes. This removes the duplication between the columns and, hey, look at that, the tables become square. Character theory proves that there are always exactly as many independent irreducible characters as there are conjugacy classes. As I mentioned in that earlier video, conjugacy classes are totally boring for abelian groups like C4. You see, commutativity allows you to shuffle the crusts of the sandwich together, and then they just cancel each other. This puts each group element in a small conjugacy class all by itself. Boring! But at least this confirms that the tables for abelian groups that we looked at in the previous video satisfy exactly the same rule. The number of irreducible characters, or rows in the table, is the same as the number of conjugacy classes, or columns in the table. And in the abelian case, this is also the same as the number of group elements. Everything still works exactly as before. Oh, and because conjugate elements have the same character value, characters are called class functions. Those are defined as functions that are constant across a conjugacy class. In physics, when you have a quantity that is constant under the symmetries of a system, those quantities are, by definition, conserved. So class functions can help us discover new conservation laws, which makes them a big deal in physics. Now let's see how many miracles we can discover in our new square character tables. Remember that each column is now a conjugacy class, and each row is still an irreducible character, containing the traces of the irreducible representation matrices. First, let's check orthonormality. We have to sum over all group elements, not just over the conjugacy classes. You often see character tables mention the sizes of the conjugacy classes at the top. Since the character values are the same across the class, we just count the value that many times. The resulting dot product turns out to be 0. You can verify a few other cases yourself. The characters are all orthogonal to each other. So even now that we use traces, the first miracle still works. If you take the dot product of a character with itself, you get 1, just as before. Don't forget to divide by the size of the group at the end. We can even show that the irreducible characters are the only ones with a norm equal to 1. If you start from a larger representation which isn't irreducible, and you write down the traces, the resulting character will have a norm different from 1. This gives you an easy mechanism for checking whether a character is irreducible or not. You can show that the inner product of two characters is always an integer, even if the numbers in the table are real or even complex. This is true for all characters, not just the irreducible ones. Given that the character table is always square, and its rows are orthonormal, you can think of the table itself as a new orthogonal matrix. Just stop and think about how crazy that is. We started from a large set of matrices, we summarized each with a single number, its trace, we placed all those traces into a table, and now this table itself turns out to be a new matrix. It's a matrix of matrices in a way. To me, this feels like, say, you're living in a house and you go through the front door to go outside, and you discover that you're not actually outside. You're now in a much larger house that's filled with houses. Anyway, this is not just a whimsical perspective. The character table really is a matrix. If you want to find out what it does, you will have to watch the Patreon exclusive video, where you will learn that this matrix plays a very familiar role, one that we have actually already talked about before. There are plenty more miracles hiding in these tables. Look at the first column. These are the character values for the neutral element of the group. Because a matrix representation must always be a homomorphism, it must map the neutral element to an identity matrix. And the trace of an identity matrix simply adds up a bunch of ones on the diagonal. So it always gives you the dimension of the vector space on which the matrices act. The short version is that the first column always gives you the dimensions of the representations. D4 has a bunch of one-dimensional and a single two-dimensional irrep. This means that the first column always contains integers. And these integers in turn have a number of interesting properties. For starters, it turns out that when you square these dimensions and add them up, you always get the size of the group. For abelian groups, all of the characters are one-dimensional, so in order to reach the size n of the group, you're going to need n of those ones. This confirms once again that the number of irreducible characters for an abelian group is equal to the group size. And there's another miracle. Each of these dimensions by itself is a divisor of the group size. 2 divides 6. 2 divides 8. This will be true in general for any character table. I like to think of this as the Lagrange theorem for characters because it's very similar to the Lagrange theorem for subgroups and cosets that we looked at earlier. Wait, there's more. The total number of one-dimensional representations in the table is 2 for D3 and 4 for D4. These counts are also always divisors of the group size. I have been calling all of these properties miracles because they are totally unexpected. It's remarkable that the trace produces so many strong patterns. Of course, there are proofs for all of these properties, but they typically go way over my head. You can read more in the many links I've left in the description. While you are there, take a second to like the video and subscribe to the channel. Thank you. Okay, we have time for one more miracle. Let's look at the regular representation again. Each group is a group of permutations, and we can easily represent those with permutation matrices. This morphism that maps each group element to its permutation matrix is called the regular representation. It is always reducible. I already showed you that a vector containing only ones is an eigenvector of any permutation matrix. So we can always split off the trivial representation. What is totally unexpected, though, is that we can split off many other irreducible representations too. In fact, it turns out that the regular representation contains all of the irreducible ones. It falls apart into a direct sum in which each irreducible representation appears at least once. How many times does a sub-representation appear in the sum? Well, that number turns out to be exactly equal to its dimension. So the one-dimensionals appear exactly once, the two-dimensionals appear exactly twice, and so on. The regular representation is like the periodic table in chemistry. It contains all the primitive elements from which the other representations can be synthesized, like molecules. It serves as a catalog for all the irreducibles. Together with the miracles of the character tables, This gives you yet another tool that you can use to find all the fundamental parts. The main point of all these amazing properties is that they allow us to find all the irreducible characters for a group. Imagine that you've already found the first 4 rows in the D4 table. You want to complete the table, but you have no idea what the matrices in the remaining representations might look like. But you don't actually need those matrices at all. You know that the table must be square, so you have only one more row to fill. You also know that the squares of the dimensions must sum to the size of the group, which is 8. Your sum only reaches up to 4 so far, so you're missing a single character whose dimension must be 2, because 2 squares to the missing 4. That allows you to fill in this 2 in the first column right away. You can then use the other miracles to fill in the rest of the numbers. You could use orthonormality, or what I've called the Lagrange theorem, or you could use a regular representation. So even if you don't know all of the irreducible representations yet, there are so many constraints on them that you can often find them with a bit of clever tinkering. The power of characters becomes apparent in physics. Whenever you have 2 physical systems, and you want to know if they satisfy the same set of symmetry laws, you calculate their character tables. If the tables are the same, you know that the representations are also the same. You don't even have to calculate any of the matrices explicitly. Just use all the miracles to complete the table, and you will know what kind of system of physical symmetries you are dealing with. This brings us to the end of the series on representations and characters, or at least almost to the end. Because if you're dying to find out more about the connections with Fourier analysis, remember that there's a video available exclusively on Patreon. Just follow the link in the description, set up an account, and start watching. Characters are functions that map group elements to scalars. In the next series, we will introduce a similar idea in a different context. We will look at functions that map vectors to scalars. Those functions are called one-forms or dual vectors, and they are the central concept in tensor algebra. If you want to start watching that series before it appears on YouTube, you can already do so right now by becoming a patron. Thank you for your support, and I will see you soon.